Hey, Algebra 2 Honor students, this is going to be our last day of Unit 5, and it's going to be on complex numbers. So complex numbers sound like they're going to be complicated, but they're actually things that we've been working with already. It is a number in the form of a plus bi. And a lot of things that you'll see sometimes will say, express your answers in simplest a plus bi form. So a plus bi form is what we'll now come to know as a complex number, where the first number is a real part. Okay, so the value of a is just some real number. And then there's a real number attached to I, which we know I is the imaginary component of that complex number. So something that's actually pretty cool about complex numbers is we can graph them. And I know that you might have to hit pause to catch up to where I am in the notes right now, but once you do that, we're going to go ahead and sketch these just kind of real quickly on a set of axes here. So we're going to sketch the complex number 3 plus 2i, negative 4 plus I, negative 3i, and then 1 minus 2i. And it's going to have a similar feel to how we plot x, y coordinate points. But technically, since we're looking at a whole new set of numbers, we need a new set of axes to be able to sketch these. So I'm going to call the x-axis, the horizontal axis, the a-axis. This is going to be where we account for our real numbers. And then I call the vertical axis the bi-axis. So this is what we'll use for our count for the imaginary piece of these complex numbers. So if we think about 3 plus 2i, the idea here would be that we have to go to the right 3, that positive direction, and then we have to go up 2. So it sort of has a correspondence with the coordinate 3, 2, if you think of it that way, in the xy coordinate plane. However, complex numbers are actually sketched as vectors from the origin. So it's not enough just to put kind of a point at 3 comma 2. It would actually be the vector drawn right here. It has a specific length and it goes in a specific direction. So vectors are something that you will study next year a lot more in pre-calc honors. So being exposed to them a little bit in Algebra 2 honors is never a bad idea. But here's what we have for this vector. This arrow doesn't indicate that it goes on forever. The arrow is simply there to indicate the direction that we're headed in. So just to kind of label this, I'm going to label this as A, because I'm going to graph them all in the same set of axes here. Negative 4 plus I, if I go 4 to the left, 2, 3, 4. And then we have to go up 1 on the imaginary axis. That would correspond with this location right here. Okay, I'm just going to turn my paper for a second. Okay, so there's my vector negative 4 plus I. I'll label that one as B. Okay, so we could probably do these pretty easily, but then, oops, we get into something like negative 3i. What's that going to look like? Well, if there's no real component, this is technically just a purely imaginary number. It's not technically complex, but we can make it look complex by writing it as 0 minus 3i if we want to. So we're not going to go left or right at all, but we're just going to go down 3. And that's what C would look like. Negative 3i is a vector straight down, right on top of the vertical axis there. And finally, the last one, 1 minus 2i. If I go to the right 1 and down 2, it's right about there. So the last of my vectors looks something like that for D. So they're actually pretty easy to sketch once you get used to the pattern. And we're not going to do much more with that idea other than graph them, but like I said, in the future, you might be studying vectors more in future math courses. So having seen this even just once and briefly at that, hopefully it gives you a good sense as to building upon this idea in the future. What the main point of today's lesson will be is talking about operations with complex numbers. And the operations that we're going to talk about are things like addition, subtraction, multiplication, and division. So let's start with the operation of addition. If I said, what's 4 minus 7i plus 8 plus 2i? It'll be pretty easy for us to add complex numbers because all we're going to do is we're going to add the real parts. We're going to add the imaginary parts, and that's going to be our final result. So 4 plus 8 in this case is 12. Negative 7 plus 2 is minus 5i. And that's pretty much it. The sum of these two complex numbers would be 12 minus 5i. So that will be something that I think Going forward, we can do fairly easily. Negative 3 plus I minus 6 minus 5I. So subtraction is going to be very similar. You can add the opposite, right? If you want to distribute that negative in, that might be a good idea. So just to kind of break this down into one more step, I'm going to distribute that negative throughout and make it minus 6 with a plus 5I. And then combining of like terms here, negative 3 minus 6 is negative 9. I plus 5I is now plus 6I. Okay. Now, in the end, when we simplify these, we really are looking for answers to be in A plus BI form. So that may not seem like as big of a deal in the addition and subtraction, but we're going to get to other cases later on where we might have to do a little bit more in terms of the algebraic work to get it to look like A plus BI form. Maybe even in this next example with multiplication, if we do 2 plus 3I times 5 minus 2I. All right, so in order to multiply these, it's completely up to you. If you're a box method person, go for it. Do some box method off to the side. If you're a FOILer, then go ahead and try FOIL. And actually, that's what I'll do right now. I'm going to do the first, the outside, the inside, the last. So 2 times 5 is 10. 2 times negative 2 minus 4I now. The inside, 5 times 3 is going to be plus 15I. And at the end, just be careful with this last pair. It would be minus 6. And then I times I is I squared. Okay. We definitely have some like terms in the middle we can combine. So we get 10, and then negative 4 plus 15 is a plus 11I minus the 6I squared. And students kind of look at this and they're like, oh, okay, well, the squared terms usually come first and they do some rearranging. And that's not really the case here, right? So it's not a quadratic that we're lined up with here. It looks quadratic, looks like we have an I squared, we have an I. Remember, I is something specific. I is an imaginary number. And more specifically, I squared has a value that we know. So thinking back to our last lesson with powers of I squared might be the most important one to remember. I'm not sure. Might be up for interpretation, but I think many other teachers would probably agree with me that knowing I squared's value is pretty critical. Comes up a lot in operations. I squared is negative 1. So then we get 10 plus 11I. Negative 6 times negative 1 is a plus 6. Making my final answer for this one 16 plus 11I. So now you can see it's in that A plus BI form. You know, it's a good hint that when you get to this stage, you're not exactly done if you have I squared still in your answer. It's not yet simplified as much as we can make it. So we'll always replace I squared with negative 1 to get to this final step where we have something in A plus BI form. All right, so if we can do addition and we could do subtraction and we could do multiplication, well, I'm guessing we could do division, right? So let's go ahead and try a division example. So as far as dividing goes, let's try something like 5 minus 2I divided by 3 plus 4I. Okay. In order to divide complex numbers, it's going to use a strategy that we're already familiar with. Whenever you're dividing, we don't like dividing by things that are imaginary, just like we don't like dividing by things that are radicals in the denominator. And that's kind of your big hint. When you're dividing, the idea is that you will multiply by the conjugate, just like we do for radicals. So as a reminder, what is the conjugate? And by the way, it's the conjugate of what's in the denominator. We're trying to eliminate the value of I in the denominator there. The conjugate of the denominator is 3 minus 4I. It's just changing that middle sign. Don't change anything else except for the sign in the middle. Okay. And now that I've changed that middle sign, I can go ahead and do some multiplication here. Okay, so again, remember, it's going to just require some FOIL, or if you're a box methoder, go ahead and do that. So in the FOIL process, 5 times 3 on the top would be 15. 5 times negative 4 minus 20I, then a minus 6I. The last term is going to become plus 8i squared. Okay. In the denominator, remember when you do conjugate pairs, you'll get the outside inside to cancel, these two middle terms. Just to show you the whole process, I'll do it for this one where I do 3 times 3, which is 9. The outside would be negative 12i, and the inside is positive 12i. So those middle terms definitely cancel, and that will always happen. The last terms would be negative 16i squared. Okay. So if you want to, could you just do the first and the last product? In my opinion, yes. Okay, but if you're unsure about that process ever, just do the whole FOIL. All right, so on the top we get 15 minus 26i in the middle, and then plus 8i squared. And then the bottom is 9 minus 16i squared. So why does this process guarantee that we no longer have I in the denominator? It's because we know that I squared from the last example has a value of negative 1. So we're going to go ahead and substitute in negative 1 for those I squared locations and continue to clean this up a little bit. So we get 15 minus 26i, and then that would become minus 8 up top. The bottom is going to become 9, and negative 16 times negative 1 is now plus 16. 15 minus 8 is going to give you a 7 there. 9 plus 16 in the denominator is 25. And we're pretty much done. We've simplified as much as we can. We've combined all the like terms. But remember, our whole goal is to get this into that A plus BI form. And it doesn't exactly look like that yet in its current state. So traditionally, what you'll see happen is that once you get down to where you've combined all the like terms, separate this into two fractions where you divide each of them by 25. So the final answer, you'll see 7/25, that's your value of A, minus 26/25 I. And I realize it's not the nicest looking complex number with those fractions for A and B, but definitely not a big deal for us in the end just to make that quick separation. That is something I'm expecting to see from you in order to get an answer in A plus BI form. So we'll watch out for that moving forward. Okay, let's try and do a little bit more with these operations by extending this to some other concepts that we're familiar with, such as multiplicative inverse. So what is the multiplicative inverse? Of, let's do negative 2 plus 3i. All right. So to figure out the multiplicative inverse of negative 2 plus 3i, I guess we have to remember, what does multiplicative inverse mean? The multiplicative inverse is what you would multiply this quantity by to get the multiplicative identity. Oh man, multiplicative identity, I guess, what number in math do you multiply by something to keep its identity the same? And I'm hoping that that's jumping out to you that the answer is 1, right? So what I want to figure out is, what do I multiply this negative 2 plus 3i by such that the product of this and its inverse are going to give you 1 as a result. It's going to return the multiplicative identity. And in math, what we do is we actually just find the reciprocal of this value, right? So if you think of something a little bit easier, like what's the multiplicative inverse of 3? The multiplicative inverse of 3 is 1/3, because 3 times a third is 1, which is the multiplicative identity. Anything times 1 is itself. So I can do something really similar for complex numbers. I can say it's just 1 over negative 2 plus 3i. But now if I look up here, I'm like, oh, wait. We can't leave i's in the denominator. We just talked about this process for dividing complex numbers. So the only thing you're going to do is, once you write that your answer is 1 over negative 2 plus 3i, this is not yet in simplest A plus BI form. Students sometimes stop here and they're like, yeah, that's the answer. And technically you're right, but it's not in simplest form yet. So multiply by the conjugate of the denominator, negative 2 minus 3i, top and bottom. What's kind of nice here is that 1 times negative 2 minus 3i is just negative 2 minus 3i. In the denominator, those are conjugate pairs. I'm going to use my little cheat method of just doing the firsts and the lasts. Negative 2 times negative 2 is 4. 3i times negative 3i is minus 9i squared. If I simplify this just a little bit further, we know that I squared is negative 1, so we've got to make that replacement. And negative 9 times negative 1 is now going to become 4 plus 9, which we know is 13. Okay, so we've done a lot of good work here. We started with the multiplicative inverse, which is just the reciprocal of this. To simplify, multiply by the conjugate, just like we did in the last example. Make sure we always replace I squared with negative 1. And then in that final step to get this into A plus BI form, we're just going to separate this by dividing both of these terms on top by 13. So negative 2/13 minus 3/13 I is the multiplicative inverse of negative 2 plus 3i. And you should be able to check that by multiplying these two things together and confirming that you get 1 as your result. Okay, to save some time, I won't make that check happen right now. But if we have a multiplicative inverse, we also can talk about questions with additive inverse. So let's talk about what is the additive inverse. Of negative 3 minus 2i. So additive inverse, I'll tell you, just in general, will be a little bit easier for us. Because remember, for additive inverse, we're trying to add two things together. And if they are additive inverses, we get the additive identity, which is 0. So if I start with that number 3 again, and I say, well, what's its additive inverse? It would be negative 3. It's just the negated quantity there, right? Because 3 plus negative 3 is 0, which is the additive identity. So when we give something that's in a complex form, negative 3 minus 2i, its additive inverse, I'm thinking about what can I add to that such that the answer is 0. And the easiest thing for us to do then in this case is actually just then to change both of these signs. So it's going to be the number 3 plus 2i. And you can confirm that by saying, well, yeah, negative 3 plus 3 is 0. Negative 2i plus 2i is also 0. So therefore, the additive inverse for this example is 3 plus 2i. And that kind of throws us off our game a little bit. Why do I think that? Because we've been dealing a lot with this idea of the conjugate when we're talking about dividing. And conjugate, I've really been really specific about just changing the middle sign. Don't change anything else. But when we're talking about additive inverse, we're talking about something a little bit different here. We're talking about what makes it such that these two things add up to 0. And that does require us to change both of those signs. So it's just something that we're going to have to carefully pay attention to moving forward. Am I changing the middle sign because I'm looking for the conjugate? Or in this specific example, additive inverse has us change both signs to get the correct answer here. Okay. All right, maybe just a little bit more practice before moving on here. Let's actually do a little bit more simplifying radicals. So we'll do something like square root of negative 180 plus the square root of negative 75 minus 4 times the square root of negative 5. Okay, so just a little bit more simplifying here, and then maybe we'll just throw in one more extra practice with some operations just before to make sure we have a really solid foundation of these concepts here. All right, so if you want to get started, you could actually remove all of those negatives from underneath the radicals as I, right? Because the square root of negative 1 we know is I. And I don't always do it this way. But for this example to start, I'm actually going to take the square root of negative 1 out of each and every one of these terms and just write it out on the outside of the radical as I. So now that I can really focus my attention on what perfect squares go in evenly to each of these. I probably am not going to have to worry too much about this 5 at the end. This is already in simplest form. If I get a 5 trapped underneath of any of the other radicals, I'll be able to do some combining in the end. Turns out the biggest perfect square that goes into 180 is 36, and it goes in 5 times. And the biggest perfect square that goes into 75 is going to wind up being 25, and it goes in 3 times. Okay, like I said, this one at the end is not going to change. So if I keep going and simplifying here, this becomes 6i radical 5 plus, then in the middle, 5i radical 3 minus 4i radical 5. And the final step here is to think about, can I combine any of these as like terms? So just be a little bit careful about that. The answer to that is yes, but there has to be the same number underneath that radicand. And the only two that we have that with is the first and the last terms. They both end in radical 5. So 6i minus the 4i out front give you 2i radical 5 plus 5i radical 3. And that's as far as we can go with that. We can't really simplify that any further because these are different numbers underneath the radicand. So we're going to stop there and say that that is now in its simplest form. Okay, if you're ready for a challenge, and I think you are, last example that we're going to do today, number 8, we'll do 4 plus I squared, that quantity, times 1 minus I, times I to the 54th, times 3 times the square root of negative 9. Oh boy. Okay, I would recommend actually giving this a shot. I know it looks a little complicated, I know it looks scary, but I would hit pause at this point, see how good you are at being able to simplify all these terms, and then in the end, multiply them all together to get one final answer in a plus bi form. It has to look like this in the end. We can simplify all of this, even with really large exponents, right? There's rules associated with powers of I that we can use there. All right, I'm going to start going through my solution. So if you want to give it a shot, now's a good time to hit pause and try it on your own. 4 plus I squared, you got to do some box method or FOIL there to get the following. You're going to get 16 plus 8i plus I squared. That's what that is. Okay, times 1 minus I. I'll hold off on that for now. I to the 54th, you have to think about how many times does 4 go into 54 evenly? Because remember, it's all about the new remainder that we get. And it turns out 4 goes into 54 evenly 13 times. 13 times 4 is 52. So this would actually wind up being a remainder of 2. And now that we know that that has a remainder of 2, I to the 54th would correspond with I squared. So that's a quick simplifying step there. 3 times the square root of negative 9. The square root of negative 9 is 3i. So breaking this down one step at a time here, this would be a good initial step for us. All right, let's go over here. I squared, isn't that negative 1? So if I know that's negative 1, this is going to magically change into 15 plus 8i. It looks like magic happened to get from here to here. But you should know that if I squared is negative 1, I'm just combining it with that there. Oh, and by the way, I guess this I squared is negative 1, isn't it? So I can make that replacement. And 3 times 3 would make that a 9i at the end. All right, let's kind of keep cleaning things up. I'm going to multiply these together. And again, that's box method or FOIL. Maybe I'll multiply those. That's just negative 9i, so that's pretty easy. So if I keep going, we get 15 minus 15i plus 8i minus 8i squared. Okay, and then, like I said, over here we get negative 9i. I'm going to save that for a little while until the end. Let me clean this up now. Just a lot of good practice with multiplication rules, some good powers of I practice. All right, so in the middle, that would be 15 and then minus 7i. Remember, if I squared is negative 1 times negative 8 is a plus 8 there, times negative 9i. Clean this up to get 23 minus 7i times negative 9i. We're getting there. Okay, now we're up to this stage where we're close, but we have a little bit more multiplication to do. It's just distributing this across, right? So negative 9 times 23, that might be a good quick calculator step. So that's negative 207 is what that is. Negative 9 times negative 7 is positive 63, and we get I squared there. Okay, is this an A plus BI form? Not yet. Because we know that I squared is negative 1. We're like a half step away from getting the final answer here. Oops, that was supposed to be a 3. 63 times negative 1. So 63 times negative 1 is negative 63. So in A plus BI form, I'm going to put that negative 63 first. The final answer is negative 63 minus 207i. Wasn't that fun? I don't know. Hopefully you got the right answer if you tried it on your own. Definitely some complicated steps along the way. I shouldn't say that they're complicated. We just have to be careful about the process, really be confident with our powers of I. These new rules with multiplication, look how many times I squared pops up along the way. That as long as we're confident that that's -1, we should be able to simplify this, no problem in the end. All right, that's it for your last lesson in Unit 5. Have a great rest of your day.